Hello, my name is Peter Yamout. I will be presenting parallel vertex cover algorithms on GPUs, and this work was done at the American University of Beirut. I'd like to start by defining minimum vertex cover. A vertex cover of a graph is a set of vertices whose deletion from the graph results in an edgeless graph. For example, we have this graph. The vertices highlighted in blue are a vertex cover of this graph. If we remove them, the graph will have no edges. A minimum vertex cover of a graph is a vertex cover of the graph with the smallest number of vertices. For this graph, we have these two minimum vertex covers, which have size 3. The typical approach to solving minimum vertex cover is to use a branching or search tree algorithm. The root of this search tree would be the full graph, and then going to the left, we remove the vertex of maximum degree, and whenever we go to the right, we remove the neighbors of the vertex of the maximum degree. And when we remove a vertex, we add it to the vertex cover. So let's take, for example, the previous graph. The vertex of maximum degree is C. Going to the left, we remove C. Going to the right, we remove the neighbors of C, and this creates a vertex cover. We continue on the left branch, and we remove A, which is the maximum degree vertex. Going to the right, we remove the neighbors of A, and that gives us a vertex cover of size 3. And then we do the same thing again. And the minimum vertex cover of this graph is 3. It is also important to note that the search tree is narrow and highly imbalanced. Prior work's approach to parallelizing this branching algorithm was to assign subtrees to thread blocks at a fixed starting level, and having each thread block traverse its subtree by a depth first search using its own stack. So taking this search tree, for example, the starting level is at depth 3, and we assign thread blocks to each subtree. The disadvantage of this approach is that nodes before the starting level are redundantly visited by multiple thread blocks. So we can see here, thread blocks 0 and 1 visit the same nodes until they get to their subtrees. Parallelizing the branching algorithm comes with some challenges. The first is extracting massive parallelism to utilize the GPUs. The second is load balancing. If we take, for example, the search tree from the previous slide, a possible solution would be to start at deeper levels. In this way, we can extract more subtrees, which will give us more parallelism to utilize the GPU, and more blocks, which will balance the load across SMs. But we will be visiting more nodes redundantly before the starting level. Our proposed solution to this issue is to use a hybrid approach. In this hybrid approach, we have for every thread block, it has a local stack. And then we have a multi-consumer, multi-producer global work list in which the thread blocks will use to distribute work between themselves. When we want to get work from this global work list, we check the stack. If the stack is empty, we get work from the global work list. If the stack is not empty, then we finish the work that we have in the stack. And when we do work, when we process a node, after we process a node, we create the children of this node. One child will keep for ourselves to solve, The other child will need to push either to the global work list or the local stack. And in order to decide, we check the number of entries in the global work list. If they're below a certain threshold, we push to the global work list. If they're above the threshold, then we push to the local stack and we solve it ourselves later on. And this behavior is the same among all thread blocks. And we took the implementation for the global work list from the following paper. The third challenge to parallelizing the branching algorithm is that memory is a limiting factor to parallelism. The search tree is traversed by the blocks in a depth-first search manner. So we need to store the intermediate graphs of unprocessed nodes. Each thread block will store its unprocessed nodes in a stack, and the stacks will be stored in global memory, which means that we must store intermediate graphs compactly to not limit block occupancy, and we need to adapt block size and number of blocks depending on the graph size and memory available, because the size of the stack depends on the size of the graph. To solve this issue, we use what we call degree arrays. So the original graph is stored in CSR format, which has storage space big O of V plus E. We made what we call a degree array, which stores the degrees of all the vertices, and it has storage space of big O of V. And the degree array, it stores the degrees of the vertices, and for the deleted vertices, it stores their degree as -1. So it also stores what vertices have been deleted. And we can use this degree array and the original graph, which all the thread blocks will have access to, and there will only be one copy on the kernel, in order to check the structure of the intermediate graph that we have. When processing a node, we implement reduction rules. The literature has many reduction rules, but we only implement 3. The first reduction rule is the leaf rule, in which that states that if we have a leaf or a vertex of degree 1, we can remove its neighbor because its neighbor will cover its edge and its own edges, other edges. The second reduction rule is the degree 2 triangle rule, which states that if we have a vertex of degree 2 and its neighbors form a triangle with it, then we can remove its neighbors because its neighbors will remove all the edges between all 3 vertices and their own edges. Last, we have the high degree rule, which states that we can remove vertices with degree higher than the remaining number of vertices to exceed current best solution. So for example, if we have this graph, the current best solution, let's say, is 3, we can remove the center vertex, and which has degree 4, and this is because removing its neighbors cannot give a better solution than 3. Onto the evaluation. We implemented 3 implementations of the problem. The first is the sequential implementation, which is implemented on a CPU with a single thread. The second is the stack-only implementation, which is implemented on the GPU, where subtrees are assigned to blocks at a fixed starting level, similar to prior work. And last, we have our hybrid implementation, where blocks offload branches to a shared global work list. The hardware used to test everything. For the CPU, we used an AMD EPYC CPU with 64 gigabytes of main memory. And for the GPU, we used a NVIDIA Volta V100 GPU with 32 gigabytes of device memory. For the problem formulations, we implemented 2 problem formulations. The first is the minimum vertex cover formulation. The second is the parameterized vertex cover formulation, where we need to find the vertex cover of at most size k. And during testing, we set k to 3 values, minimum -1, minimum, and minimum +1. To evaluate performance, we run every combination of formulations and implementations over 18 graphs, which are categorized into high-degree graphs and low-degree graphs, and we report the aggregate speedup. And you can see the individual speedups and runtimes of every graph in the paper, in a table in the paper. The first observation we can make over these results is that the hybrid outperforms the stack-only implementation substantially on high-degree graphs and moderately on low-degree graphs. This is because high-degree graphs have higher imbalance when branching. The second implementation we can make is that, observation that we can make is that hybrid outperforms stack-only substantially on difficult long-running instances and moderately on easy short-running instances. And this is because difficult instances perform wider search and are more likely to encounter deep branches. The third observation that we can make is that the hybrid outperforms sequential substantially on difficult long-running instances. And this is because there is enough parallel work exposed to benefit from GPU resources. To evaluate load balance, we ran all the implementations and combinations of implementations and formulations on 2 graphs. One is a high-degree graph, which is the p-hat 1001, and the other is a low-degree graph, which is the US power grid graph. These results show the number of tree nodes visited by an SM. The first observation that we can make is that the stack only has higher load imbalance on high-degree graphs than low-degree graphs. The second observation we can make is that stack only has higher load imbalance on difficult long-running instances than easy short-running instances. And the third observation we can make is that hybrid achieves better load balance than stack only, which explains why hybrid is much faster on longer instances. On to evaluation of the breakdown of execution time. Here we have these results show the percentage of total execution time on different graphs. We grouped the different execution times into 3 groups. The first group is the execution time that is related to work distribution and load imbalance, node balancing. The second group is execution time related to reducing. And the third last group is execution time related to branching. The first observation that we can make is that the kernel spends 24.1% of its time on work distribution and load balancing, of which 16% is spent removing from the global work list due to high contention and or waiting for empty work list to receive work. The second observation we can make is that the kernel spends 65.2% of its time on reduction rules, which is well spent because reduction rules make fast progress towards the solution. The third observation we can make is that the kernel spends 10.7% of its time on branching, of which 9.4% is spent on removing the neighbors of the max degree, which is larger for high degree graphs. In summary, vertex cover algorithms traverse narrow and highly imbalanced search tree. We propose to use a hybrid approach with per block local stacks and global work list for extracting parallelism and dynamic load balancing. We implemented efficient memory management, which is key for not limiting parallelism. And we were able to achieve substantial speedups over prior GPU approaches that only use per block local stacks. And all the code is available on my GitHub account in the following repository using the following link. Thank you for watching.